Here's an example, actually two examples of finding the area of a triangle from SAS data. So a side, two sides, and the included angle. And it's another great example, not even a particularly complicated use of the idea of take an unright triangle, drop an altitude. Sometimes you have to choose exactly which one carefully, and then you get right triangles and you use trig in some number of steps. Here it's actually not going to be that many steps. So the task here is to find the area of this angle, area of this triangle. We know the angle at A, 43.41 degrees. I had the geometry software just measure these for me, so they're actually accurate. AB is 5.35 and CA is 2.44. We want to find the area of that. So we just drop an altitude, and we want to drop an altitude so that we get at least one right triangle where we know a side and an angle. And dropping it from C is totally going to work for that. So we're going to drop that from C. Let me bring that pre-made picture up here. An altitude from C to AB. And voila, we get this new picture. That's distracting. Let's get out of there. And so let's say H, just an abbreviation for that CD. And that's going to be the height of the triangle. And we're almost going to be done once we get the height of the triangle, because the area of that triangle, soon we're going to be doing even more complicated area stuff, but right now we just know that the area is, let me just call it area, is 1/2 base times height. And that's going to be 1/2 times 5.35 times H. Okay, so compared to some of the multi-step problems we have done and we're going to be doing, this is actually really quite chill. But I wanted to make sure that it was something you can do on your own. And so how would we get the height? We just have in this right triangle, we have the hypotenuse, and the height is the opposite of the known angle. And so that's going to activate sine of that angle is equal to H over 2.44. You can go ahead and get that sine out of the calculator right away, but I tend to do it just a little bit, sort of show how you can delay that. And in particular, that means you can do this all in one line on the calculator. No worries about getting a partial answer, writing it on paper, rounding it, putting back in the calculator, and kind of over rounding things. This is just going to be completely in one line, and that is about 1.677. Okay. And then we're almost home free, as I pointed out. Area is 1/2 times 5.25. And I could just copy that in, but you know what? I'm going to show you again how you could get the most accuracy out of this. This is something you could actually do in one line on the calculator. So if you want to do it in the most accurate way, just assemble all the ingredients and do that all in one fell swoop on the calculator. Not incredibly important. We could definitely take that and put it in here, and that's 4.402. And at that point, we're probably going to go ahead and round to something a little bit less. Okay, so I want to point out one variation on this, and it's a very important thing about the general procedure of dropping altitudes, and that is you can drop altitudes outside a triangle. What you're really doing when you drop an altitude, even in these examples, I'm really creating a segment from one vertex that's perpendicular to the line containing the other side. Here, it actually hits the segment that is the other side. But here, I can still take, so here's a little different. I didn't change this side, but this is now opened up to be an obtuse angle. This is a little different because I just moved it on the dynamic geometry program. But the main thing is that this is obtuse. And if I drop a dotted line perpendicular to the line AB, it doesn't actually hit inside the triangle, but it totally hits the line. And so let me show you that. Okay. And so we still get this thing. It's still the height of the triangle. That's absolutely still called the height of the triangle relative to the base AB. And we just have one extra step that we're going to have. So we still get a right triangle here. It still has a known hypotenuse. Now it's 2.54. And we just have to do a tiny little observation to get the angle in this triangle. Let you think about that for a second. If I know this big obtuse angle, how are we going to get that? And that's just the fact that the whole thing together makes a straight angle, or a 180. And so that angle CAE in the new right triangle is 180 degrees minus 138.93 degrees. Okay, and so that's 41.07 degrees. Okay, and now it's extremely like the previous. We now know that sine of 41.07 degrees equals h. We still call that height h. I don't know what that. Okay, so that's CE now is the height over 2.54. Now h equals 2.54 sine 41.07 degrees, and the area. So we'll show you the slick way again. 1/2 times the base. Make it more explicit. Times all this stuff. You can kind of see we're kind of deriving a master formula, kind of a shortcut formula. And if you want to kind of figure out what that shortcut formula is and memorize it, that's fine. I really want us to focus on the core skills and how to use them in multi-part situations. But this is a pretty straightforward formula, especially once you realize that getting that angle is not hard at all. And there's even some more shortcuts you learn later, but I think we'll save those. So this one is 4.464, and I'd say 4.5 maybe for our usual kind of rounding. Okay, and that's it.